I want to look today at the mechanism of acid catalyzed addition to carbonyls, because once you've mastered this one set of mechanistic steps, you can write the mechanism for at least 5 different types of reactions. Even though they don't look like the same, they really are the same. So we're going to be looking at reacting some compound with a carbonyl group in it, a C double bond O, and reacting it with some sort of nucleophile, which is represented as Nu here, in the presence of H+. And most of the time in these reactions, our nucleophile has some kind of hydrogen attached to it. Whenever you're given this set of conditions, the first thing that's going to happen is that the lone pair of electrons on the oxygen are going to react with the H+. This is going to give us our protonated carbonyl compound. I can draw a resonance structure of this where the electrons in this double bond move up onto the oxygen, giving me a structure where the positive charge is on the carbon. Now my nucleophile can come and react with the carbon that has the positive charge on it, giving me a structure that has both the nucleophile and this OH attached to the same carbon. What's going to happen next is the oxygen is going to pick up a hydrogen. We could draw it picking up a hydrogen from the H+ in the reaction, or we could just show that the hydrogen on the nucleophile transfers to that oxygen, and that's what we're going to draw. When the oxygen picks up this hydrogen, it's going to become positively charged, and the nucleophile is going to lose the positive charge because it gets the electrons from the bond with that hydrogen. Now this oxygen is part of a good leaving group. It was OH over here, which would be a bad leaving group. Now it's H2O, which is a weaker base in a good leaving group. So it leaves with the electrons in this bond. This gives us water plus this carbocation. Well, we can do a couple of things with this carbocation. One of the things we're going to do is we're going to draw a resonance structure of it where the lone pairs of electrons on the nucleophile come down and help stabilize this carbocation. This resonance structure puts a positive charge on that nucleophile the way I've drawn it here. The other thing that can happen is another one of our nucleophiles can attack this positively charged carbon. When this happens, I end up with a carbon that has 2 of my nucleophiles attached to it, with one of them, the one that just attacked, still having a hydrogen and a positive charge on it. Well, we're going to lose that positive charge when something removes that hydrogen, some sort of base. It could be the water that was lost. It could be another one of the nucleophiles. It could be the conjugate base of this acid. Whatever it is, some sort of base present in solution removes that hydrogen, giving us a product with 2 nucleophiles attached to this carbon and no charge. Well, why did I go through this whole process? Because it turns out by changing the nucleophile to different things, we can use this mechanism for a bunch of different reactions that we've talked about. For instance, if this nucleophile is an alcohol, and I'll just choose a simple alcohol like methanol, and I change nucleophile, the Nu, all the way through my mechanism to an alcohol like methanol. So I replace my nucleophile with methanol all the way through the process. I end up with a mechanism for formation of an acetal. On the other hand, if I replace my methanol with my nucleophile with an amine instead of methanol, like methylamine, so I'm going to replace all of these with methylamine, I get essentially the same thing all the way through until this point. So all the way through to this point, I've replaced my methanol with my methylamine, showing the addition of methylamine, losing water here to get to this resonance structure. But at this point, instead of another nucleophile adding to this carbocation and following this pathway to the end that we did before, we lose the second hydrogen from my amine. I'm not going to draw arrows to show it, but it's probably a base, probably another molecule of the methylamine that comes in and takes this hydrogen. And we end up making my imine. So this, by making those few changes, replacing the methanol with my methylamine, shows how we get to an imine. Similarly, if I replaced my methylamine with hydrazine, So I'm basically replacing this CH3 with an NH2 and made that substitution all the way through. I now have the mechanism for forming a hydrazone. So same steps, just replaced my CH3 with an NH2. I also want to look at how what we've been talking about can be used to explain a slightly different mechanism. In this case, I'm going to replace my R with an OH, and I'm going to make my nucleophile methanol again. And everything's going to be the same in my mechanism up to right at this point where I have this resonance structure. But instead of having another nucleophile come and attack my carbocation, I'm actually going to draw a third resonance structure of this molecule where the electrons, the lone pairs on this oxygen, come down and help stabilize this positive charge, giving me this structure, which when I lose the hydrogen, the extra hydrogen from this oxygen, there's some base present in the solution, maybe another molecule of methanol that removes this hydrogen. I end up with this structure, an ester. So this is the mechanism for Fischer esterification. And the mechanism for Fischer esterification is the same as the other mechanisms we've talked about up to this point where we drew this extra resonance structure. If I make one more change and change this OH all the way through my reaction to an ethyl group, or an ethoxy group I should say, everything is going to go exactly the same as before up till this step where the hydrogen goes to a different place. Instead of going to this oxygen with the OH, it goes to the oxygen of the ethyl group. Meaning that this time it's the ethoxy group that has the positive charge on it, and it's this group that leaves. And I lose a molecule of ethanol this time, but I get the same intermediate I had before in my Fischer esterification, and everything proceeds exactly the same way through the rest of my Fischers, through the rest of my reaction to my final product. And in this case, instead of being Fischer esterification, this is transesterification. The only difference being that this picked up my hydrogen instead of this oxygen, so this group left instead of a water molecule. The last thing I should point out is all of these steps are reversible in equilibrium, so I should draw arrows going in the opposite direction as well to indicate the equilibrium. And that means that the mechanism for the reverse of this, whether it be hydrolysis for a Fischer esterification or going from my methyl ether ester to my ethyl ester, the steps are just reversed for this. So one mechanism, we based all of these mechanisms that we talked about today off of this one general mechanism of a carbonyl being protonated and a nucleophile added to it. So I strongly suggest you learn and feel very comfortable with this general scheme and then use it and adapt it in the slight ways that we adapted it to each of those other mechanisms we talked about.